Okay, we're going to be taking a look at activation energy and reaction mechanisms. From reading the chapter, you should be familiar with activation energy. It's that little mountain between the reactants and the products. So these would be called reaction coordinate diagrams. It's showing the energy in a system as you go from the reactants to the products. So this would be an exothermic process here. You started at high energy, you ended up at lower energy. But to do it, to get to here, these guys have to pick up some energy first. Before the reactants can turn into products, they have to gain energy. Sometimes we think of that energy as coming in the form of a collision. So as two things slam into each other, they pick up some energy and it allows the reaction to occur. So activation energy, it's that energy it's that little mountain you have to get over in order to turn into products. Now, keep in mind, reactions are reversible. So these products here, these products could pick up a whole bunch of energy and turn back into reactants. Just as these reactants here can pick up a little bit of energy and turn into the products. So, bottom line is, the smaller this mountain is, the lower the activation energy, the faster the reaction goes. Now, you all know that catalysts make reactions go faster. All a catalyst does, really, to make a reaction go faster is it lowers that activation energy. So in the presence of a catalyst, the activation energy is lower, and let's face it, climbing a small mountain goes faster than climbing a high mountain, and that's why catalysts work the way they do. Now keep in mind, with all of this stuff in kinetics, you never change the energy level that you start with and the energy level that you end with. This number right here, that's delta G, the change in free energy from here to here, that never changes. The only thing in kinetics that you can mess with is the size of the mountain in between. That's the activation energy. Now, reaction mechanisms. Let's take a look at reaction mechanisms. Reaction mechanisms are stepwise processes that explain how a reaction occurred. A lot of reactions do occur in one step. Everything just slams together and you get your products. Sometimes it's a stepwise process. So in this hypothetical reaction, two molecules of A react with a molecule of B. They produce a molecule of E and a molecule of F. Now, you might propose the mechanism this way. You might say, well, I don't really think that all three of these things slam together at once and just boom, turn into the products. Maybe it's a stepwise process. Maybe first one molecule of A combines with a molecule of B to give this product. We'll call it C. Then that guy, C, bumps into another molecule of A and it produces another intermediate, D. And then D kind of decomposes and gives you the products. That would be a three-step mechanism. Each individual step here is referred to as an elementary step. Now, when you're looking at a mechanism, make sure you can identify so-called intermediates. Intermediates are species that are created over the course of the reaction, but they're not really products. So, in this mechanism, A plus B react to give C. Well, C is not one of the starting materials. C is not one of the products. C is an intermediate, as is D. D is another intermediate. Now, if your mechanism's a good mechanism, if it's the true mechanism, You can never prove it's a true mechanism, but if it is the true mechanism, when you add up all the steps, it had darn well better add up to the overall reaction. So if you were to add all these 3 steps up, let's see. Do you see how C cancels out? D cancels out. Add up all of the things on the left side of the arrow. You have 2 molecules of A plus a molecule of B, and they're reacting to produce E plus F. So if nothing else, your mechanism had better add up. If you add up all the elementary steps, you'd better get the overall reaction. Now, other stuff you need to know here about a mechanism. The rate law for an overall reaction is determined experimentally. We beat this to death in other lessons. There's different ways of determining the rate law for a reaction. That's called the observed rate law. You measure a rate law, and keep in mind that in an observed rate law, this guy up here, there's not necessarily a relationship between the order with respect to A and this coefficient. They may be the same, they may not be the same. So X here might be 2, it might be 1, heck, it could be 1.5. For B, the order in B, we're calling it Y, it might be 1, it might be 2. The only way to know those reaction orders for the overall reaction is to measure those things. And you get what's called the observed rate law. Now, the weird part is for an elementary step, it turns out the coefficient matches the reaction order in that species. So for this elementary step, because it's an elementary step, I can write the rate law for that elementary step. The rate law for step 1 is K1 times the concentration of A to the first power, concentration of B to the first power. Hey, for the second step, since it's an elementary step, I can say the rate for the second step equals that rate constant, we'll call it K2, times the concentration of C to the first order, and the concentration of A to the first order. And for the third step here, your rate for the third step would be your rate constant 3 times the concentration of D to the first order, since there's only a 1 there. Boom. Now, this bugs people. You just have to go with the flow here. Trust me, for an elementary step, if it's a single step thing, yeah, the coefficient from here has to match the reaction order. For the observed rate law, no, those coefficients don't necessarily match. Alrighty. Think of it this way. I like to think of it this way. The observed rate law is reality land. This is real. That observed rate law is something we measured in a lab. It's real. These rate laws are sort of fantasy land. We're saying we think maybe this is a mechanism that explains everything, and we know that we could write these rate laws if this reaction occurs, that would be the rate law. But we don't know that it occurs. It's fantasy land. So, next thing to know is if a mechanism has more than one step, one of those steps is the so-called rate determining step. It's simply the slowest step in the process. So the slow step in a mechanism is going to be called the rate determining step. And here's the deal. If the proposed mechanism is correct, the rate law for the slow step will be the same as the observed rate law. Suddenly, reality land, fantasy land match. It doesn't mean that the mechanisms necessarily true, it just means that it's not false. The depressing part of studying mechanisms with kinetics, I've known quite a few people who do this for a living. I never understood these people. I think it's depressing as all get out. You can never prove that a mechanism is correct. All you can really do is prove that a mechanism is incorrect. If the rate law from the proposed mechanism does not match the real rate law, that mechanism's garbage. Let's say the two rate laws match. Well, it means maybe your mechanism's right, but maybe it's not. That's checking mechanisms with kinetics. Let's take a quick look at an example or two. Let's take a look here at this situation. Say we have our overall process, or overall reaction. Two molecules of this react with the B, they give us the products. And we measure the rate law. This here is the observed rate law. Observed or measured rate law. And let's say we propose this three-step mechanism. And we say that the slow step here happens to be this one right here. The very first step is the slow step. Remember, that slow step is the rate determining step. So if I write the rate laws here, the rate law for the first step is the rate of that first reaction is equal to some rate constant, we'll call it K1 times A. That coefficient's a 1, so it's A to the first power, and it is B to the first power. Now, you might want to stop the video just for 30 seconds. Make a judgment. Is this mechanism consistent with the observed rate law? So, well, the rate law from the mechanism is first order in A. The real rate law is second order in A. So the answer there had better be no. Basically, this mechanism is garbage. It's not a correct mechanism. This mechanism does not explain this reaction. So you can prove a mechanism to be incorrect. Now, one more quick example. Let's say same setup. Sorry, I keep using A, B, E, and F. You'll find a lot of people that do kinetics work, they always talk in terms of A, B, C, D, E, F. Quite often they won't write the actual chemicals down. It's odd. Anyway, so let's say you got this reaction again, and again, here's your observed rate law. Observed rate law. Second order in A, first order in B. And you say, boy, I think it occurs in these three steps, but the second step is the slow step. The slow step would be the rate determining step. So for this mechanism, the rate law that goes with this mechanism would be the rate for step 2, the slow step, is going to be rate constant 2 times the concentration of C and the concentration of A. C to the first power, A to the first power. So, stop your camera for a little bit here, or stop your video, and ask yourself, is this rate law consistent with this rate law? Okay. Now, I'm willing to bet that most of you got the wrong answer here. Is the proposed mechanism consistent with the observed rate law? Most of you probably said no, because, gee, it's second order in A, and this rate law is first order in A. But guess what? The correct answer here is yes. This is consistent with this. And you might be going, wait, how can I say that? How are you saying that? Rate equals K C to the first, A to the first is somehow the same as rate equals A to the second times E. How are those two the same? Well, here's the deal. This rate law, the one we took from the mechanism, is expressed in terms of the concentration of an intermediate. It's really important to recognize intermediates. So this intermediate C can't be in, you can't have C in the final rate law, but you know what? You can solve for the concentration of C. Solve for the concentration of the intermediate in terms of reactants. And the way that works is you make what's called a steady state assumption. You assume that anything above the slow step reaches equilibrium. If this is the slow step in the process, then this reaction here, the first reaction, will come to equilibrium. You can then write an equilibrium expression for that, and you can solve for the concentration of your intermediate. So for this first step here, for that very first step, for step 1, you can write an equilibrium expression. So for step 1, you can say the equilibrium constant K is equal to the concentration of C all over the concentration of A and the concentration of B. So again, I'm just taking the concentration of this over this. And I can write an equilibrium expression because anything that takes place before the slow step reaches equilibrium. Now, we can take this equation, this equilibrium expression, and we can solve for the concentration of C. Why don't you stop the video right here, stop your video, and see if you can take this equilibrium expression and solve it for C. Okay, restarting the video, you can say, okay, let's see, I want the concentration of C. Well, the concentration of C is going to be equal to the equilibrium constant times the concentration of A and the concentration of B, right? So, if I express C, the concentration of C, as this times this times this, if I simply replace C with that, see, we got our rate law from the mechanism, R2 equals K2 times C to the first power, A to the first power. And of course, from the previous page, we found that the concentration of C is given by K times A times B. All I'm going to do here is replace this term. I'm going to replace that term with all of this, and we'll end up with rate 2 equals some constant K2 times, in place of C, I'm going to have K, A, and B. So all of this is him, and I still have this A. That A is that one. Hey, a constant times a constant is just another constant. But if we look at the reaction orders, this is clearly second order in A. So the whole thing's going to be K2 times the big K times A to the second power times B. Hey, it is A to the second power, just like in the observed rate law. So this mechanism here could potentially be a correct mechanism, because the rate law we end up with is consistent with the observed rate law, second order in A, first order in B. Quick look at catalysts again. One last look at catalysts. Slide this up. You know that a catalyst makes a reaction go faster, so it will increase the rate of reaction. It does this by lowering activation energy. And at the start of this, in my notes, you'll see this in a lot of textbooks. I'll show you. Here's your uncatalyzed reaction. Here's your catalyzed reaction. So clearly the activation energy has been lowered. What they sometimes don't tell you is the way you lower the activation energy is you allow the reaction to go through a different mechanism. It occurs by an entirely different mechanism. So maybe you take a one-step process and you turn it into a two-step process. So if this is your uncatalyzed reaction, so to get from reactants to products, you got to climb this great big mountain in one step. Maybe you have a catalyst that allows a reaction to go in two steps. One step that's got a activation energy. The second step has a even smaller one. Hey, going in two small steps has a lower overall activation energy than going in one big step. So that's the way catalysts work. And another big thing to keep in mind with a catalyst, they're not unidirectional. Your catalyst doesn't just catalyze reactants going to products, it catalyzes products going to reactants. So if you make the forward reaction go faster, you're also going to make the reverse reaction go faster. All a catalyst does is it makes everything go faster. The reaction will come to equilibrium faster than it did before. A catalyst can never shift the position of equilibrium. From the chapter on thermodynamics, you know that the position of the equilibrium is determined by the delta G. That'd be that guy there. The difference between reactants and products, that's delta G. And notice, in the uncatalyzed or the catalyzed, delta G is the same for both of them. So, a catalyst will never change delta G. It will not affect the equilibrium constant. It will not affect the position of the equilibrium. It'll just make you reach equilibrium that much faster.